change. It's a pleasure to have you around for today's meeting. I'm Christoph and I will be chairing the meeting. The structure of it will be the same as always. We start with a roughly 40 minutes talk, followed by a Q&A, and ending with a feedback and discussion section with Carl. And I can see, Carl, you have already started the recording, so I do not need to remind that. And today I am delighted to introduce Professor Tamas Spisak. Professor Spisak is a professor at University Hospital in Essen, Germany, with a research focus on predictive and computational modeling based on neuroimaging data. And today he will talk about attractor dynamics and active inference. So without further ado, I'll pass it on to you, Professor Spisak. Thank you very much for joining us today.
Yeah, thank you all for your interest and for your time. So I'm really eager to talk about this topic, attractor dynamics, and how they implement large-scale information integration in the brain. This topic lies pretty close to my heart, especially in the last 1 year, since I have started to work on the math under this or behind this whole idea. And yeah, I might be a bit longer than 30 minutes. Sorry for that. I will try to keep it concise, but there are really a lot of things I would like to share with you. So if you think about emotions like happiness, fear, anxiety, or about pain, self-reflection, high-level cognitive functions, or like going a little bit more abstract, different modes of operation in the brain, then these have at least one thing in common. They all require and rely on integration of information from many different sources in the brain. For instance, pain, where I have a specific background actually, so I did a lot of pain research. And it is clear that pain is not merely a response to incoming nociceptive, so painful stimulation, but it entails the integration from other sensory channels, as well as internal states like contextual cues, memories, goal-directedness, expectations, and so on. And as a result, the same nociceptive stimulus can cause very different pain experiences, as we see it in placebo analgesia, or in certain types of chronic pain where there is no nociceptive input at all, and the patient still feel pain. So there are many theories about how this high-level information integration could happen in the brain. And I won't go into the details here. There is at least one thing in common in these theories, and it is that most of them agree that there must be somewhere an irreducible subsystem in the brain that has access to all the relevant information that is required to compute or to construct that specific experience or function. However, these theories largely disagree about where this high-level information integration happens in the brain. Candidates range from higher-order cortical areas like the prefrontal cortex or parietal or temporal association areas, or a network of these, or sometimes the brainstem or the hippocampus is mentioned. But what we can say for sure, that in general, exactly this type of experiences and functions which require this broad level of information integration. So these are exactly the ones that are pretty hard to map into any of these regions or even to a network of these. There is another very promising but often overlooked candidate for where information integration could be located in the brain. And these are network dynamics that organize around multiple stable states, known as attractor states. And attractor dynamics have long been proposed to play a significant role in information integration and related topics at the circuit level. So at the circuit level, it's very well known as a concept. It's very often used, and it became an established model for several canonical brain circuits involved in like motion integration, memory, decision making, spatial navigation, or you can also think about the ring attractors to encode directions. It also seems to be clear that such multi- and metastable attractor dynamics extend to the macro scale in the brain. So these do not only exist on the circuit level, but it's a bit less clear what they do. So you can often see statements like they accommodate the coordination of heterogeneous elements at the macro scale. But I find these statements a bit vague. And I think in general, we have a less detailed understanding of how these high-level integrative computations are or could be implemented by attractor dynamics. So today I will try to shed light on this with a prototypical mathematical formalization, and then I will continue with some empirical evidence for that. In this mathematical framework or mathematical formalization, I will start from this. I hope you can see my my pointer. So I will start from this little guy here, which I guess I don't have to introduce to this audience. So just very quickly, here eta and mu are the external and internal states, and they are connected by the sensory and active states which introduce conditional independence between them. And as we know, as long as this conditional independence, this specific conditional independence structure persists over longer temporal scales, the mu state will perform inference on the eta by minimizing free energy. So as a next step, I will assume that eta itself is not directly accessible. We can only access certain aspects of it and only measure those. So that we have to build up this hierarchical structure where information from these distinct sources is first inferred by lower level states, which I denote sigma. And then these are integrated in the high level integrator node, mu. What I hope to be able to clarify today, that this type of integrative computation, which I will formalize, and what happens in mu has an intermediate relation to attractor dynamics. So I start from a simple and convenient parametrization of this system, where the integrator node, so this will be the integrator node mu, it's a Gaussian, where so it follows a normal distribution, and the inverse of the variance of this normal distribution is the precision of information integration, and the mean of this distribution will be basically biased by or shifted by the sensory state. The lower level state, which I denote sigma, so it's not the external state here, but the lower level state, sigma, I parameterize this as a continuous Bernoulli distribution, which might be a bit unusual, but we will see why. What's the reason for that? The point is here that this continuous Bernoulli distribution represents the level of evidence for or against an event. And this distribution has a single parameter, a bias parameter, which I call B. And it can basically represent the prior for the evidence of an event. So it can basically stem from internal arbitrarily complex internal computations in this lower level node, and then the bias is shifted by the action state. To keep things as simple as possible, the sensory and active states will be parameterized as a Dirac delta distribution. So in other words, these are they just deterministically pass the state above them, and all they do is that they multiply that with a weight, which I denote with W. So the first thing we do here to keep things even more simple, that we marginalize this little guy here to S and A, so that we can focus on what sigma and mu are doing. And marginalizing this is quite simple because of the Dirac deltas, but there are also many other parameterizations with which it's not complicated. And the point is that we can have the joint distribution of sigma and mu, which looks like this. So it has three terms, one for sigma, one for mu, and one for their interaction. Then I combine many of these very simplistic or very simple systems, marginalized systems, into such a bipartite hierarchy. So that basically the higher level, so there are multiple sigmas and multiple mu's, and the higher level nodes are basically integrating the information from the lower level nodes across different or with different weights. Let's not forget that this here is still statistically equivalent to the original unit with S and A. So it means that it's not explicit here, but the Markov blanket is still there. And using this property, it turns out that it becomes very easy to write up the joint distribution of this whole system, so all sigmas and all mu's, because we can factorize the probabilities, and basically within the exponent, we can just sum them up. And what we got here is it turns out that this is a special case of a so-called restricted Boltzmann machine. So basically, a restricted Boltzmann machine is a very well-studied lecture book neural network model. And the underlying statistical mechanics are quite well understood, which is great. We can try to bring in all that knowledge to further study this system. So restricted Boltzmann machines are energy-based models characterized by the Boltzmann distribution, which is equivalent to what we have just derived here. Or to be precise, this is a special case of Boltzmann machines. And within the energy, we still have the same three terms, one referring to sigma, one to mu, and one to their interactions. And yeah, sorry. And now comes the main trick, or basically the most important moment of this mathematical derivation. The restricted Boltzmann machine, so we marginalize the joint distribution of this restricted Boltzmann machine to mu, actually. So basically we marginalize out the higher level integrator nodes from the system. And mathematically, this is a bit delicate. This marginalization, it involves, or it relies on the cumulant generative functions of mu, which is, in our case, is Gaussian. But what we get is this here. So you can instantly see from the equation, it's a bit small, sorry, but you can hopefully see that that basically we have one term for sigma and another term for the interactions between all the sigmas. This is statistically equivalent to this one, but now we only rely in the description, we only rely to sigma. And it turns out that this exact distribution is actually describes a type of an attractor network, specifically a stochastic continuous state Hopfield network, which is, as I said, statistically equivalent to this hierarchical system, but it only consists of the lower level nodes, the sigma nodes of the system, and these higher level integrator nodes, mu, they became the attractor states of the system, interestingly. So they do not exist physically anymore in this system, but still they exert the same effect on the lower level nodes as real physical integrator nodes. So, and there is also a clear connection between the weights of these two systems, which is shown here. So this is basically a mathematical duality, and we can go back and forth between the two architectures if certain assumptions are fulfilled. And yeah, so we have started with small active inference units. So it's a question if these nodes still behave in a similar way. And I'm still working on this part. And any feedback or any remarks here would be very, very welcome. But in general, what I have done so far is that I wrote up the free energy from the point of view of one of the nodes, sigma, given all the other nodes in the system. And then if I put in the parameterization which I used, then it turns out that in free energy, the accuracy term will guide us when we are minimizing free energy. It will guide us to the minimal to those points which have a minimal energy in terms of the attractor network's internal or global energy. On the other hand, the complexity term will simply ensure that this process lands in the closest, intuitively, it ensures that it lands in the closest minimum. And you can see that this is already conceptually very similar to the update rule of the Hopfield networks. And indeed, if we take the partial derivative of this expression with regards to P, so the bias parameter, then we can easily get back to the the update rule of a stochastic Hopfield network. We even have a sigmoid function because of the distribution we have chosen for the low-level nodes. And we can get even more insights. It turns out that the temperature parameter, which is a very important parameter for Hopfield networks and in general attractor networks, so this temperature parameter can be basically derived from the precision in the higher level nodes mu, which I denoted with beta. This was quite a busy slide, sorry for that, but now I will do a quick interim summary so far. So far, I provided prototypical mathematical formulation, and I have shown that the hierarchical computing structure of little free energy minimizing units itself is also a free energy minimizing unit, and it is statistically equivalent to an attractor network, where the higher level integrator nodes became attractor states in the system. So this is my recap here at this point. And before I go further, I would like to discuss quickly the main assumptions of having this interesting duality between these two different topologies or architectures. The first is the distribution of the lower level nodes, which was this interesting continuous Bernoulli distribution. But the point here is basically that we somehow need to have a sigmoid, or need to have a distribution here, which provides us this sigmoid-like behavioral in the lower level nodes, because they will end up the nodes of the attractor network. And this sigmoid prevents the whole system from blowing up. And it also provides us all the the abilities of neural networks to model complex patterns and complex decision boundaries by this added nonlinearity. Let's talk about the Gaussianity of the integrator states. As the Gaussian distribution is the only distribution where only the first two cumulants are non-zero, and in the marginalization process, we relied on the cumulant generative functions. Therefore, all other parameterizations for the higher level node will result in systems, in attractor networks that also utilize third and higher order interactions between nodes. So not just second order interactions. But this is not necessarily a disadvantage, because actually such systems are the same as the so-called modern Hopfield networks, which is a relatively new and extremely efficient attractor network architecture with exponential storage capacity. So I think this is certainly an interesting direction to follow up on. But so far, I stick to this simple solution with the Gaussian integrator nodes. Yeah, and regarding the Dirac deltas in the boundary states, there is not much to say. I think this can be easily swept to a lot of different probabilistic or noisy or maybe even temporally lagged distributions. What might be more interesting here is that here I assumed that the weights are symmetric. So W is the same for S and for A. And this is a technical necessity for the math I used. But there is evidence that attractor networks with asymmetric weights can still remain effective. However, in general, they tend to lose some of the stability and may react chaotically to parameter changes. But in general, I think there is no reason to believe that the duality I outlined would not hold, at least approximately, even in the case of a mild asymmetry, which we know that there is in the brain. And finally, during the marginalization process, there is an other assumption, which I haven't talked about. And this is that the attractor patterns must be uncorrelated, or in other words, the columns of W must be uncorrelated, orthogonal to each other. But this can also be relaxed to a certain degree. There are some recent results in this paper which show that if these are correlated, so the columns of W are correlated, then the resulting attractor network is still very similar to the original one, but the stronger this correlation, so the correlation in general acts as a noise source, or at least it can be approximated like that, and it will cause the attractor network to be less stable, and there might be also spurious attractors emerging as there is more correlation. But this duality and the general idea should still hold in that case, at least with mild violations of this assumption. And importantly, this orthogonality assumption might be quite a reasonable one, because keeping the attractors orthogonal is one of the most efficient ways to maximize the capacity of the attractor network itself, while removing spurious states. So this is actually called projection Hopfield networks in the literature. So now let's see some general consequences of this mathematical duality I've been talking about. First of all, to me at least, it provides a fresh view on Hopfield networks and attractor networks in general, because how we usually think about these networks is that that they can store patterns during a training procedure, and then if we provide noisy variants or distorted variants of these stored patterns, then the network recalls them by converging towards its attractor states during a so-called relaxation procedure. But now having this duality with the restricted Boltzmann machine architecture, I think it becomes more clear that that the attractors are not simply the readout from this network. Those are not simply just the result of this inference process, but they are actually actively contributing to the underlying computations. So attractor states in an attractor network can do a lot of computations. For example, they can do Bayesian causal inference, which you might know from Professor Kerding's papers. And this can be very easily illustrated on this toy network, where the two low-level nodes process auditory and visual stimulations or events. And we have a single higher-level node, or in the alternative representation, a single attractor state that infers whether the auditory and visual events have a common cause. And with the provided mathematical formalization, the system automatically basically performs a Bayesian causal inference. The activity of the integrator node will represent the evidence for the common cause, and the actual causal structure is basically specified by the weights here. And then the posterior of both the visual and the auditory regions will be adjusted according to this to the degree of estimated causality. If there is no common cause, then the posteriors will be unchanged, basically. The same toy network with a minor modification can also do predictive coding. For this, all we need is an inhibitory connection here with blue. And then red is the prediction, blue is the observation, and the higher level integrator node, or equivalently the attractor state of the system, will implement or represent the prediction error in this system. And again, if we plot the prior and posterior distributions, then we can see that basically the posteriors for both the prediction and the observations are adjusted based on the prediction error. So that's all cool, but why would the brain use this architecture if basically the whole point is that everything can be done with the good old hierarchical bipartite system, which I have shown? Well, because the attractor implementation of the same network is, on one hand, obviously less vulnerable, because it has no physical integrator nodes to be damaged. Those are no attractors. And also the weights of the integration, which is like, for these systems, is kind of like the software code of the system. This gets distributed across the weights based on this equation. So if only one connection falls out, the whole system still can remain, still can behave very similarly. On the other hand, the attractor network architecture can be also more economical. In optimal circumstances, it has half the wiring cost than the full hierarchy. Or if we allow non-Gaussian integrator nodes and go to the modern Hopfield network territory, then we will have an exponential storage capacity in the network, which basically it would mean that the number of things to integrate at the highest level has no practical upper limit anymore. And finally, the attractor architecture can be trained efficiently with local learning rules, which is very important from the point of view of neurobiological plausibility, of course. So the framework and outline so far has a lot of predictions that can be tested experimentally. And I will just skip this slide because I want to spare some time and start right away with actually testing all these predictions, because we have done some initial work with fMRI data. First of all, just a few sentences why I believe that functional MRI might be suitable to reconstruct attractor states and the attractor dynamics of the brain at the large scale. One reason is that there is kind of an agreement that in the brain, the fast components of brain activity at the circuit level tend to quickly converge to this so-called inertial manifold. And then you possibly know these arguments. So the point is that, without going into the details, that large-scale attractor dynamics are very likely substantially slower than the time scales of the single neural dynamics. And they extend into the slow timescales of the hemodynamic response. So it looks like we have all the chances to catch these dynamics with fMRI. In terms of the spatial resolution, we can use the fact that the brain has a modular and hierarchical structure, which allows us to lump together those parts of the network which are functionally similar, and therefore they have a similar effect on the large-scale dynamics. In dynamic systems theory, this is called coarse graining, and actually what we do in neuroimaging, what we do with functional parcellations is, I argue, it's something very similar. So at this point, you can already probably guess that I will use regional time series, fMRI time series, to try and reconstruct these the large-scale attractor dynamics of the brain. So the next thing is to see whether we have any existing evidence in the literature for similar dynamics. What we know that in attractor networks, dynamics are generally governed by an update rule, which updates the activation in a node based on the weighted sum of all other nodes' activity, where the weights are simply the network weights. And it turns out that we have something very similar in the brain. It is called the activity flow phenomenon, and it states that the activity of a held out region can be predicted by the weighted sum of all other regions' activities, where the weights are given by the functional connectivity between these regions. So this is a very simple but quite thoroughly validated observation. And it also implies that just naively, if we initialize the network with, so initialize an attractor network with functional connectivity as weights, and apply the activity flow rule iteratively multiple times, then this system should behave like an attractor network. But it is of course a question whether using the functional connectome as weights gives us a nice and well-behaving attractor network. For example, it could happen that we have only a single very trivial attractor state, or we could also have a huge number of very unstable attractor states with small Bayesians and very poor convergence properties, or we could even get some chaotic behavioral. So we must ask these questions, and we have to see how well the functional connectome is suited to be the weights of an attractor network. This is what we have investigated in a recently published study. It's now published in eLife. And what we have found, so we did exactly this. So we took the functional connectivity as estimated basically with partial correlation across the time series, and then considered it to be a continuous Hopfield network, continuous state Hopfield network. And we have found that there are multiple attractor states with stable large Bayesians. The whole system converges very nicely, much better than different null models. And this whole thing is highly replicable across datasets. And also importantly, using this attractor network as a phenomenological computational model can reconstruct key characteristics of resting state brain dynamics. And it can also predict how this network or how this system reacts to different perturbations like tasks as compared to the resting state, or what we have, for example, investigated is pain and pain modulation, and how the network can capture the changes in dynamics. Importantly, the attractor states also seem to be pretty much in line what we already know from the neuroscientific literature in terms of neurobiological relevance. So like, for example, here you already might be able to see something very similar to the default mode network, but let's talk about this a couple of slides later, because I very quickly would like to introduce another approach to reconstruct large-scale attractor states. This is an analytical approach, and this is based on the duality between attractor networks and restricted Boltzmann machines. So first of all, the mathematical theory or framework I have shown you suggests that the weights can more precisely be estimated by the negative inverse covariance matrix between the time series of the network. And then, and then we should remember that the attractors of the system are the higher level nodes in the restricted Boltzmann machine. So mathematically, this basically means that the attractor states must be only an orthogonal transformation away from the eigenvectors of the functional connectome, as specified by the negative inverse covariance. And when we take into account our assumption regarding the orthogonality of the attractor states, then we have a unique solution, which are the eigenvectors themselves. And this gives us the opportunity to contrast these two approaches. So we have one approach this is a slow computational approach with quite some technical difficulties and sensitivity to noisy measurements, but with no assumption on orthogonality. And we have another lightning fast and stable analytical approach, but it takes use of this orthogonality assumption. So we can just contrast the two, and if they provide the same results, that can be considered as evidence for the orthogonality assumption. And basically, this would be the this would provide a strong evidence for the validity of the whole mathematical duality I outlined in the beginning of the presentation. So this is a very important thing to investigate. So we have investigated it in resting state fMRI data, and it turned out that the strongest attractors are very similar with these two approaches. So this is the computational, this is the analytical. And per definition, the analytically derived attractor states are orthogonal to each other. But as you can see, they are very, very similar to the computationally derived attractor states. If you don't believe your eyes, then we can also look at the angles between the attractor states. So as I mentioned, for the analytical approach, per definition, from the multiple solutions, we choose the one where there is perfect orthogonality, but there is no such assumption for the computational approach. And we get this, which I would say it's not a bad result. The computationally derived attractors definitely seem to be orthogonal to each other. And you also have to take into account here that we have, so this is a very initial analysis, and we have started based on population average connectivity matrices. So inter-individual variability can certainly mess up things at this point. In the next step, we will use precision neuroimaging datasets from a single individual to try to make this cleaner. But finally, let's have a more detailed look on the attractors themselves. Here are the first six attractors as reconstructed with the analytical approach. So basically the eigenvectors. And as you can see, so importantly, the first one, per definition, is basically the eigencentrality of the functional connectome. I think it can be interpreted as inferring to what degree information has to be broadcasted in the brain. And then we have other attractor states, which, as you can see, pretty much resemble to the default mode network or other canonical resting state networks, like I don't know, dorsal and ventral attention networks, and so on. And however, it's very important to point out that at this point, these are not simply descriptive features of the data, like, for example, with ICA components. But by using the duality to the hierarchical topology of the restricted Boltzmann machines, these maps can be interpreted as the weights for an invisible integrator node that infers a high-level causal relation, as shown on or depicted by these graphs below. And then the whole system infers multiple of such relations in parallel, and the invisible integrator nodes act back on the brain regions to achieve the optimal posterior bias in them. So this can be made clear by this. So basically, the proposed framework provides a brand new interpretation for what functional connectivity is as measured with fMRI. In our framework, functional connectivity between two regions can and should be decomposed into weights of integration towards these large-scale attractors. Furthermore, we can also try to reconstruct the underlying energy landscape of the system. Here I did it with the TSNA, and you can see that the attractors are in the local minima of this energy landscape. Of course, I don't say that in reality this is a two-dimensional energy landscape, but this might be a good estimate for a low number of attractors, I believe. And reconstructing this high-level energy landscape has, of course, important implications for approaches that try to conceptualize various behavioral or clinical states and traits as features of the underlying dynamic system. For instance, in chronic pain, chronic pain could be conceptualized as a malformation of the energy landscape itself, due to which the system is more likely to infer painful states and struggles leaving the corresponding pathological energy minima. Let's skip this. And yeah, finally, within the proposed framework, next to the time series of the lower level regions, which we measure with fMRI, because of the duality, we can also reconstruct and calculate the time series of the attractor states of the system. And interestingly, based on some recent results by Rosas and colleagues, it turns out that attractor networks perform integrative calculations based on the similarity between the present and stored patterns at this level. So yeah, basically, in other words, the attractor time series and computations, what happened there, constitute an emergent level over the lower level nodes time series. In order to predict what's happening in the attractor domain, we don't have to know about the lower levels. The lower levels can provide additional information, but in order to understand what's happening at the upper level, we don't have to know the lower level. And of course, with this, we could empirically test to what degree a certain function is implemented in attractor states of the system, because we can just see whether we can achieve a prediction or a predictive performance as good from the higher level or the attractor time series as good as from the lower level time series. Here I have some initial results for this. Here you can actually see an attractor time series. And here I just show that the attractor time series do capture different aspects of pain and non-painful heat stimulation. But for the sake of time, I will skip it now and just close with this slide, where I just wanted to highlight that this emergence property may have also implications for neuroscientific and philosophical accounts for investigating consciousness. I'm not an expert of this field, but I know that there are recent efforts to conceptualize consciousness in terms of the Markov blankets of the system. And if the brain is an attractor network, then our formalization outlines a very interesting Markov blanket in the brain. Actually, I think it's the largest Markov blanket possible, because it incorporates all the regions in the brain and separates the attractors from each other, from the lower level nodes, and from the external world. So I will leave you with this for now, and I will very quickly summarize the take-home messages. I might be a little bit out of time, sorry for that. So the take-home message is that hierarchical integrative computations can be implemented in attractor states. And this seems to be a plausible model. Attractor computations constitute an emergent level over the lower level computations. We can actually, so we have initial evidence that we are able to reconstruct these attractor dynamics from neural measurements. And I believe they hold promise for a better understanding and for the modeling of the neural underpinnings of various behavioral or clinical states. Thank you very much. I just finished with my thank you slide.
Amazing. Thank you very much, Professor Spisak, for this brilliant presentation. Everyone, please a quick unmute and applause. And then we can lead over to questions. Yeah, please raise your hand if you have questions. We can also just let it all settle for a minute. Otherwise, I just have a maybe bit of a naive question. In the beginning, you were talking about irreducible subsystems. And I was just wondering sort of whether you could maybe elaborate on that a little bit more, because I guess the minimization process leads to attractor states. And these attractor states are irreducible because they emerge from the entire network's interactions, and like sort of they can't be achieved by any subset of the network alone. But I was just wondering sort of where does this irreducibility stem from? I guess mathematically, it's logically and coherent, like from the conceptually from the other perspective. How do we know that it is these systems are irreducible, or where does this come from? Could you maybe elaborate on that?
Yeah, so of course, to answer that, we have to agree upon a good definition of what irreducibility is. But I think what guides my thinking about this is this paper I also referred to by Rosas and colleagues. This is a recent, I think it's just a preprint yet, or maybe it has already been published somewhere. They provide a computational definition. It's called computational closure. And this is kind of a mathematical way to pronounce or to spell out emergence, and also to some degree irreducibility. And this is where on one of my last slides, as you also mentioned, I ended up at this conclusion. So basically it says that that computations in the attractor domain are irreducible in a sense that it's kind of a minimal set which is needed to predict the results of those computations which arise from there. And of course, it's a question how well we can actually measure those, because of course, to the point where everything turns again into behavioral, there might be a lot of things added by the lower level systems. But at least in theory, this is what happens in Hopfield networks. And I think it's very easy to generalize to different types of attractor networks. So it's not a question whether attractor state computations in the attractor domain are emergent and irreducible in an attractor network. The question is whether the brain is an attractor network, for which I hope that I have provided some convincing initial evidence.
Thank you very much. And maybe also you want to go back to that slide on the active inference in Hopfield networks, because I remember you mentioned that you were hoping maybe to get some feedback on that. Okay. Just if anyone has some thoughts on this, feel free to share, and we'll just maybe wait another minute, and otherwise.
Do you actually see my slides?
At the moment, well, we see a screen, but not the slides.
Okay, background. Then yeah. Then wait a bit, please.
It is a very cool picture, though.
What about now?
Yeah.
Great. So I can quickly add some more detail here. So as I mentioned, I just started to work on this, and like probably there are many of you who for whom it's much more comfortable to move with all these equations. I'm just discovering the whole thing, but I somehow have the gut feeling that there are many interesting things buried here. For example, I suspect that maybe minimizing expected free energy will be actually somehow bring out the training part of the network. So how actually the weights should be changed in order to better adapt, or in general becoming a free energy minimizing machine that does this job even better. But this is this is just a gut feeling for now. This is definitely something that I would like to go towards, and basically that's the current state.
Then maybe this is a good point. Unless someone else has something to say, they can say it now. Otherwise, I think it is your turn now, Carl.
so soon.
It appears so.
Right, excellent. Okay, well, it was a very impressive presentation. Excuse me. So I noticed you had Christian on as your first collaborator. So is he a key collaborator of yours? I think we've.
Yeah, he should be. Oh, yeah, he's just joining back now.
Sorry, it's my bad. I just clicked
worries.
the wrong button.
Are you with us again? Oh, you're
Yes.
here twice
Yes, I'm
now.
here again. It was my bad. I unfortunately or unintentionally I closed Teams, but now I'm back.
Oh, I see. Good. No, it's just that my screen has you here twice, which is interesting. Let's.
Yeah, maybe I can remove the other one. Yeah, I'll try that.
Oops. Yes, well done. Excellent. Good. Then it shouldn't get confused. Sorry, I was just congratulating you on an excellent presentation and asking
Oh, thank you.
What your relationship with Christian Buchel is. Is he a colleague or?
Yeah. So we are involved in a grant, and we are linked in many ways. So basically, he was the supervisor of Professor Bingo, where I was a postdoc before. So we are involved in a lot of common projects, and we are in a very strong collaborations at many sites.
Excellent. Well, give him my very best wishes. I saw him a few months ago, actually. Yeah. Anyway, yeah. So there's a lot of material here, and yeah, it was very good of you to share all of this with us. I'm going to try and just pick out a few key notions that impressed me, and you can read that as the sort of paper that I think will have an impact in my world or in my community. I'll also, as you were talking, I was going through sort of picking out papers that I'm familiar with that would speak to some assumptions, some ideas that you presented. So after making a few comments, I'll just go through those papers because they remind me the points that I wanted to make. But just standing back, yeah. To what extent have you written all of this up? Have you published over the past few years on these ideas, or are you amassing material in order to prepare a number of papers?
Yeah, so there is a paper out, but it's not at all about this mathematical background. It's just the initial empirical observation. So it's just started with an empirical observation in resting state fMRI data. And then I started to work out the mathematical background. And now I can also see that in the first paper, I was wrong in a couple of things. It's in eLife, so I might still have the chance to correct those. But the second write-up, it's already online. It's not on any preprint server, but I just host it as a publicly accessible web page. Maybe I can quickly link it here. So it's kind of, yeah. So I think if you will look at it, I don't know where the chat is in Teams. Maybe someone can help me out.
Yeah, it should be in the top section next to, I mean, I'm not sure whether we're seeing the same thing, but it should be at the top bar in the very most left icon. It says chat. And I think you can just share it in there.
All right.
Do you see that?
No, unfortunately. I see all the participants and everything.
Otherwise,
maybe I can just send it afterwards in a mail. So if you will look at that, maybe then it almost looks like a paper. but I didn't make a preprint yet because I was kind of working in isolation on the math, and now I'm on the quest of collecting feedback
I see.
to find the right points. So and afterwards, probably early next year, I would like to finalize this write-up. But that's why I'm eager to hear your thoughts. What type of paper would, for example, you personally like to see, or how would this whole topic affect you the most?
Right. So, I mean, that's an excellent question because that's exactly the kind of feedback which we're meant to deliver. I think probably best approached in terms of the basic messages and the people or the communities that would appreciate those messages. And there are a number of levels that you could, or there are a number of messages or stories that you could identify, and therefore different kinds of journals. Even when you're pre-printing on archive, you'll still have to identify, is this neurobiology, is this machine learning, is this data analysis? So it would be, I think, useful just to tease apart the different levels of analysis and implications, ranging from inner screen notions of consciousness right through to center manifold theory. There's a whole range of things. So people talking about consciousness and the inner screen model are unlikely to know about center manifold theory, and vice versa. So I think you have to sort of emphasize different parts of the story. For me, the two most important parts were the demonstrating or joining the dots or making links between a universal particular partition that underwrites the free energy principle. So noting you didn't actually use the free energy principle, but you did start from the same starting point, which is a particular partition into internal and external and interface or boundary or Markov-Blanket states. I think that's an important move. And then from that, you were able to derive the special cases that emerge under certain assumptions as Hopfield nets and restricted Boltzmann machines. So I think that just as a simple observation is very important. Just saying that you can take a universal partition of the states of any complex system, any sparsely coupled dynamical system, random dynamical system, if you like, and show that with some plausible, not minimal, but they're plausible assumptions, that so certain kinds of systems now have exactly the same functional form as in the first instance restricted Boltzmann machines, and in the second instance as Hopfield networks, which enables you immediately now to talk about self-organization in far from equilibrium systems, cast as random dynamical systems. You can now talk about that self-organization in terms of exactly the same kind of attractors that you'd find in attractor networks, auto-associated networks, Hopfield networks, and indeed the teleology of inference and learning associated with restricted Boltzmann machines. So I think that was an important, so that was the first half of your presentation, basically, just showing that if I just assume this, this, and this, then the functional form of the dynamics of this system suddenly re-emerge in exactly what you would have been reading about 20, 30 years ago in restricted Boltzmann machines, and the exception of Hopfield networks and the like. So I think that's very important. And then I notice, sorry, that is one story. And then you've got another story. If we make the same assumptions for coupled neuronal dynamics and treat the brain as a sparsely coupled dynamical system, and we then apply this in the context of characterizing and data analysis, the ensuing eigenmodes now inherit exactly the same interpretation that the attractors do in the context of this. It's not even theoretical, it's sort of more, well, theoretical physics versus theoretical biology treatment of self-organization in non-equilibrium or non-equilibrium steady states. And that this, so that means that the second story, which is about characterizing dynamics in the brain in a particular way now inherits a link to or a functionalist interpretation in relation to computation under generically the particular petitions upon which the free energy principle is based, but also there's special cases such as restricted Boltzmann machines and ultimately Hopfield networks. So I think teasing them apart, but at the same time, because you've got this one pillar, which is the computational story, distinct from the other pillar, which is characterizing biological time series, means that you can now appeal to the other pillar in saying that we've done more than just do an eigen decomposition of fluctuating Bolt signals. We can now interpret these eigenmodes in terms of attractors, and indeed mathematically under certain assumptions they stand in for the estimates or the latent states, the internal states. Although they are invisible, they are latent, but they stand in for or can be read as the latent states that are compressing all the dynamics on the Markov boundaries or Markov blankets, because you've established pillar one first. So I'm suggesting you do it the other way around. You do your archive computational physics, non-equilibrium physics self-organization, and then say applying the same assumptions to data analysis. Now that affords a much richer and diverse interpretation of what these modes mean, even to the extent you could actually claim that the whole literature over the past 20 years now on intrinsic brain networks and so default mode, dorsal attention, salience and attention networks and the like. These are just the reason these have been so popular is that they do have a functional interpretation. So, to my mind, what you were showing in terms of the high-level attractor states were just the expression of the intrinsic brain networks. They're just the expression of the principal components, ignoring the twists you get if you move to an independent component analysis, which means that you are now able to equip an interpretation of the default mode with a formal interpretation that it is just basically the expression of the probability of it being in this attracting state or that attracting state, and in the spirit of a Hopfield network, in the spirit of a Waddington landscape, or whatever story you want to tell. So I thought that was an important an important story, but it is a distinct story. You'd be writing that for
exactly.
Yeah, it might be eLife. Well, yeah, I suppose a bit of neuroimaging gets into eLife, and it's a lovely millennial, if not Generation Z kind of publishing. But there are other specialist journals that say the New Imaging Neuroscience, or Neuroimage, or Nature. They have one for imaging. I don't know. Anyway, I would say you could be speaking to people whose daily life, like Christian, is trying to make sense of neuroimaging and biological time series. That probably wouldn't, be burdened with quite the same maths and function and mathematical derivations as your more neural computation, biological cybernetics, right through to nature machine learning kind of publication. Just because I've mentioned biological cybernetics, a lot of your arguments, I think, could also be linked to cybernetics in the original sense, but also self-organization under synergetics. So the slaving principle is one way of interpreting what you were talking about in terms of these invisible latent modes, or if there's a duality here, you've either got an integrator node, I think you call it,
Yes.
a latent state that is standing in for the sufficient statistics of dynamics on the outside, then and the equivalent interpretation when if you effectively integrate out those latent states so they are invisible or just implicit, but you've got the same modes on the boundary states or the external states. That sounds very much like, well, certainly the first component where you've actually got explicit integrator nodes. That sounds almost identical to the synergetic formulation of self-organization in non-equilibria, where your invisible or your latent internal states, your mu, will be known as order parameters, and they enslave the fast dynamics that you were referring to in terms of the inertial manifold, or collapsing to the inertial manifold or the center manifold, so that you can look at the latent states as defining the shape of the inertial manifold, the center manifold, and in so doing, enslaving the fast dynamics. So that's where the slaving principle of physics comes from, and that was originally developed in using Ginzburg-Landau models of laser physics, but exactly the same principles of separation in the fast microscopic, very stable modes and these slow, unstable eigenmodes that in synergetics of the Haken sort would be referred to as order parameters. So just using all of these different sort of words for the same mathematical construct, I think would serve a very useful purpose in just pulling everything together. In that spirit, I'm just now looking at that kind of joining the dots and showing the cross-cutting themes in terms of these different perspectives on self-organization, what that would look like from the free energy principle. I have to say, from the point of view of the free energy principle, it is almost tautologically true that the whole point is explaining the dynamics that attend any system that has an attracting set. So it's not that you can talk about attractors. The free energy principle is about how do you explain the emergence of attractors. So there has to be an attracting set there before there is any probability distribution. And there has to be a probability distribution before there can be a particular partition defined in terms of conditional dependencies. So you start with an attracting set, or you start with the assumption that this random dynamic system has an attracting set, and it will always converge to its free energy minima. Even before you put the partition into place. The special kind of free energy that the celebrated in the free energy principle is the variational free energy, which is a functional of the latent variables or the mu's, when treated as sufficient statistics over the external states. But the same principle occurs. The attracting sets simply are the dynamics or the solutions that minimize free energies. It's another way of describing the attractors. From that point of view, because that is the free energy principle, certainly before you actually move to the variation free energy part of it, is so universal by design. I think it would be very useful to say, look, there are some really interesting special cases that emerge from that. But perhaps we should just talk about the special cases before quickly going through the papers that allow you to motivate those special cases. The most important thing as a simplifying assumption is the assumption of the symmetry in the W's. That's the thing that makes everything work, and that is interesting because that symmetry in the W's in the simplified Boltzmann machine-like, or indeed Hopfield network-like formalism means that you have equipped this particular system with detailed balance. In so doing, you have guaranteed the emergence of point attractors. And in so doing, you can now talk about point attractors, and you can put little red circles on a Wellington landscape, based upon TSNE and the like. I think that this is quite a fundamental observation, which actually, like most things, dates back to Helmholtz in terms of the Helmholtz decomposition of any flow. including probability fluxes or probability currents. So what? There's a number of ways of looking at this, but I'll just tell you how I look at it, because I think that you'll be able to spot the same themes if you read people like Ping AO, or you read original Helmholtz, or you read people dealing with non-equilibrium steady states as opposed to equilibrium steady states. So any flow, any gradient flow, any dynamics can always be decomposed into a participative and a non-dissipative part. From your point of view, that's basically at this point, if you linearize around this point in state space, that means the Jacobian can be written down as a symmetric and an anti-symmetric part. The symmetric part is the dissipative part, and it has real eigenvalues. And when at the point that the flow is zero, that is the point attractor. That is, and those will be the eigen solutions of the symmetric part, or the real part of the dissipative flow. The other part has an anti-symmetric. So the leading above the leading diagonal is a negative of below the leading diagonal. This is known as a solenoidal part, or non-dissipative or conservative part. This leads to circular flow. So you now break detailed balance because you've introduced a non-dissipative, conservative aspect to the dynamics. I'm just going to minimize that and pretend I'm looking at you a bit more. Oh, where are you? There. So this part, you can either read this in a number of ways, and I'll show you, if you're not familiar with this literature, a paper that's just sort of taking you by the hand through this. You can either cast this part as the imaginary part of the flow if you want to work with complex flows, or complex members, or you can just say it's the conservative or solenoidal part of the flow. It is that part of the flow which breaks detailed balance. It is that part of the flow that, if sufficiently nonlinear, will lead to stochastic chaos. And I notice you mentioned that if you have a violation of the symmetry constraint, then not only will you introduce periodic or quasi-periodic dynamics. So there's still an attracting set. It's just now either periodic or quasi-periodic. And as you increase the nonlinearities, it becomes chaotic. But it's still an attracting set. It is now in a chaotic attracting set. So in principle, your generic results should still hold, even with stochastic chaos. However, you're going to lose the connection with Hopfield nets and restricted Boltzmann machines, because they limit themselves to dissipative dynamics. Another way of saying that is that if there is no conservative dynamics, then the system does not break detailed balance, and you have you can time reverse with impunity.
Thank you. That's eye-opening now. Yeah, that's very helpful. That's what you just said about the Helmholtz decomposition. And okay, now just keep on going. I just wanted to say that.
Well, it's good because if you can do this for other readers, just to say, look, these are just all the same thing, but we're just using a different language, a different perspective, to make some fundamental comments about the class of systems. Is this kind of class or that kind of class? And another way of doing this is another distinction between those systems that have purely dissipative flow with symmetric Jacobians is between equilibrium and non-equilibrium systems. So as soon as you have the solenoidal flow, you are now talking about attracting sets that attract a steady state that is non-equilibrium, because it has this itinerant, circular, and possibly chaotic aspect. So now you're talking about the physics of open systems. I mean, you were originally, because you've got the Markov blanket, but at least mathematically now, you can say now we're in the game of dealing with non-equilibrium steady states that self-organize to an attracting set that could be chaotic, and it certainly could be periodic, But if we make the simplifying assumption that we can approximate with a fixed point attractor, so, then we are naturally inducing the same kind of physics that would be applicable to equilibrium physics, which is, you know, the sort of schoolboy physics where the second law applies and the like. So, you know, you've got equilibrium, non-equilibria versus equilibria. You've got breaking detail variance versus not breaking detail variance. You've got purely dissipative versus mixed dissipant solenoidal. And just for your interest, if you take away the dissipative part, so that you're now all your Jacobians are identically anti-symmetric, that's classical mechanics. That's that's Lagrangian mechanics. That's mechanics that heavenly bodies used as they go around the sun. You know, it's all the same maths. It's just the limiting cases that you're talking about. So, framed like that, then there's a very natural way to say that, well, let's take the limiting approximation where we are now going to deliberately discount or preclude non-dissipative dynamics, so that we can now use all the machinery that applies to fixed point attractors and equilibrium steady states. Beautiful examples of this inherit from sort of 20th century neural networks. For example, the restricted Boltzmann machine and the Hopfield network. And, you know, and then say, we're going to really drill down on this. The other important, from the point of view of pillar 2, under the assumption that you've got a symmetric Jacobian, then you can associate the effective connectivity, which is the elements of the Jacobian, with the inverse of the partial correlation coefficient, if and only if that symmetry constraint holds.
Okay.
So the equivalent gift, it's a gift that you have to pay a price for, which then the price is you can't do itinerant dynamics. But if you're prepared for, you know, not worrying about itinerant dynamics at the moment, the solenoidal part, then the gift of that symmetry assumption simply is by pure linear algebra that the Jacobian just is the inverse of the partial correlation matrix. You have that equation. I think J was equal to lambda sigma to the power of 1. And that means that all the functional connectivity literature under this assumption now can be read, if they'd actually taken the inverse of their correlation matrices, could have been read in terms of the effective connectivity. And of course, the eigenmodes of the effective connectivity are just the fixed point attractors. So now you've now got, if you like, the reason why the second half of the talk works is because it seems as if the empirical data behave as if it was largely classical or not classical. It was largely dissipative dynamics, which, you know.
How do you think all these assumptions hold for the brain itself? You know, so like from many sides, I think a very reasonable critique I will receive is that these connections are not symmetric in reality. So I'm missing a very important point, and the question arises whether what I see with this assumption is that even, you know, like can that even be can that still be considered as a valid approximation? So do we learn about the system with this, or we are just missing such an important point that everything,
right, you know, well, I think that is exactly the kind of question that your section 3 of your next eLife paper would start with, and then you answer it. So the answer would be along the following lines. Obviously, at a certain scale or multiple scales, neuronal dynamics and any complex dynamical system, random dynamical system, will show will break detailed balance and show itinerant chaotic dynamics, or at least rhythms in the brain. And we know that at every scale, whether it's gamma oscillations through to reproduction or infraslow fluctuations, you know. So all of these cyclical revisiting parts of the the attracting set in some phase space are all expressions of this solenoidal non-dissipative dynamics. And I repeat, it can go from very, very fast, you know, oscillations right through to reproduction or replication in an evolutionary time scale. So we know that these the real universe breaks detailed balance, and that's the whole point of studying non-equilibrium steady states or far from equilibrium systems. However, at a particular time scale, if it is the case that some dynamics of a system converges to a fixed point, you know that there can't be any, that the attracting set does not entertain something that has an orbit or an itinerant, a chaotic, it's not a chaotic set. If it is converging to a particular state, then you know at this time scale, there is a fixed point attractor, which means that there must be detailed balance, which means that the solenoidal part of the dynamics is small in relation to the dissipative part. And I think you can easily motivate that for things like fMRI time series. So you imagine, I know that you were showing your fluctuations, but think about say the pain study with sort of placebo and real thermal pain. At the beginning of the onset of a pain, you'll get a slow change in the brain's activity, and that'll settle down to some kind of steady state. And from the beginning of the onset to the end of the block of painful stimulation, it looks as if at the scale of hemodynamics and at the sort of macroscopic scale that you're measuring neuropopulation activity, it looks as if it is converging to a particular condition-specific point attractor. So that immediately licenses you to say, well, okay, if there's a point attractor, the Jacobian must be symmetric. It must show detailed balance. If it shows detailed balance, then the effective connectivity must be the inverse of the partial correlation coefficient. And if I know that, and I can measure that because I can measure the functional connectivity or the correlation matrix, I can measure the eigenvalues and I can quantify and I can look at the eigenmodes. And I can quantify not only the fixed points associated with the the very slow modes where the eigenvalues approach zero from below, but I can also show you what this looks like in space as an eigenvector, as you did in the presentation. So I think that you can, and then remind the reader, of course, this is only appropriate description at this scale. If we now go down to the scale of millimeters and milliseconds, then I expect to see all of these brain areas showing fast gamma oscillations and nested theta gamma. And of course that you could not apply then.
I think there is a nice literature that like asymmetric networks can contribute to like sequence generation and all that stuff. I'm not an expert of that, but I know a couple of people who do that stuff of research. And I maybe I didn't get everything what you said, but I'm still a little bit afraid that people will see a circularity in this argument. Like we are starting from fMRI, which is simply not really able to resolve any asymmetries at that scale. So
no, you would see the asymmetries easily at that scale because you'd see cyclical activity. So if you're looking at resting state, there are no fixed point attractors. That's the whole point of having the slow fluctuations. So there would certainly be at that level solenoidal dynamics that had a slow characteristic time scale given by the complex part of the eigenvalue if you just took the whole Jacobian and took the eigenvalues. But what I'm saying is you don't have to tell that story. You can say that you can say that you can use an adiabatic approximation. You can say that this resting state study is not actually an itinerant orbit with a chaotic attracting set. It's actually a sequence of fixed point attractors where I've got a series of contexts where in each context we don't have any solenoidal flow, but what we do have is a fixed point attractor, and that means that I can use the data, the correlations, as I go to this or to the next one, as a way of well, let me start again. You can basically what sometimes can be thought of in terms of linear switching dynamical systems. You can say that, yes, I've got an orbit, but what I'm going to do is I'm going to assume it's an orbit which is basically converging to this, then it's converging to this point attractor, then it's converging to that point attractor and that point attractor over some suitable time scale. What I'm saying is this is how I would argue for the gift of that the simplifications that arise by assuming the symmetry of the Jacobian. And of course, it's not a necessary assumption, but it's certainly a sufficiently powerful and simplifying assumption that people like Hopfield and most of 20th century physicists committed to, because they just couldn't deal with the non-equilibrium part.
Yeah.
So it's only in the 21st century that people sort of start taking these more generic solutions seriously, and hence you get sort of physics of non-equilibria as opposed to equilibrium physics. So I think all you have to do is to say, look, from the point of view of the user and the person interpreting the data or applying these tools to interpret the data, just please remember that, yes, at some extended time scale, there will be an itinerancy here where we cannot assume detailed balance. But if you make an adiabatic approximation that for a short period of time, this system can be described as gravitating to a fixed point minima, and that gravitation is literally described in terms of a gradient flow on a free energy landscape that also has its inferential teleological interpretations in terms of the variational free energy principle, because I've used a Markov blanket, then I think you'd be fine. I'm not saying that you should spend the rest of your life working with detailed balance. What I'm saying is, if you were challenged by the audience or the readers or a reviewer to say, how on earth can you justify this simplifying assumption? That's one way of justifying it.
Yeah. Thank you. So I all these adiabatic approximation things. So I considered this in terms of like defend the temporal resolution of fMRI and show that it's a suitable method. But I didn't think at all to about basically using the same principles to argue about the symmetry as an assumption. So that's also very enlightening. Thank you.
I think, yes, I mean, you should emphasize that you're looking at the right scale here. If you were using neuropixels or electrodes, you'd be looking at the wrong scale to get this overall how the brain works. You wouldn't get the functional anatomy or the space-time anatomy of brains if you use the wrong scale. You've got the right scale with fMRI over several seconds, beyond the cognitive moment, beyond evoked responses, over centimeters and decimeters. That's the right scale to drill down this. And at that scale, I think you can assume that a discrete approximation to a chaotic orbit in terms of a succession of fixed points. There is a small literature on that. Mathematically, the image of that is known as a stable heteroclinic channel. I'll put that up. Well, let me do that because you're probably getting tired now. So I'll go through the papers. No, I won't find that. So there is a small literature on how one can cast what looks to be no, I'm afraid. Right. Sorry. Forget what I was where I was going back. I was going to explain something called stable heteroclinic channels or stable heteroclinic cycles, SHCs. And these are particular constructs which are very useful for modeling things like central pattern generators in neural networks. And basically what they have is unstable fixed points. So you're at this part in phase space, and you've got this fixed point, and you're attracted towards it. But the point is that this fixed point is unstable. It's usually a saddle point. So as soon as you get there, you're then thrown off in another direction to the next fixed point, to the next fixed point, to the next fixed point. The nice thing about this construction is up until the point you get to your unstable fixed point, it looks as if you've got detailed balance because you've got this point attractor. And then you can draw nice diagrams with exactly like you had with your circle of sigmas, where you're moving from one fixed point to the next fixed point to the next fixed point, simply because each fixed point is inherently unstable. So you get attracted down one manifold, but then on other dimensions, then it spits you out to the next one, and then to the next one, and to the next one. And then ultimately you go around in a big circle. So that's called.
What you say now is very, very similar to something I've been thinking about. So in the framework, so how I derive Hopfield networks, these are not the conventional Hopfield networks. So these are stochastic Hopfield networks. So there is, like probabilistic, all the nodes, these are not like the typical binary Hopfield network. And also and this I realized when I did this little free energy derivation with the variational stuff on like from the point of view of one sigma node. So what I realized that minimizing free energy principle is a little bit, so not exactly the same as the traditional Hopfield network energy minimization, because at every step I have to adjust the bias and not the actual state, but the bias of the probability distribution of the state. But for the next step with a different bias, I got a different energy landscape. Still in practice, so if I implement it, it pretty much works like a Hopfield like adding noise to a Hopfield network. But at this conceptual level, it's just I just felt a very strong analogy with what you say, that even if every step I have fixed points and everything is like tractable and nice, because of changing the bias all the time, and like as the network converges towards the attractor state. Yeah, so I don't know how to finish this sentence, but what you said is like really again highlighted to me something that might be very interesting. So basically from the point of view of the free energy principle, at every step of the relaxation process, it looks like the network this type of network I have specified would already arrive at the attractor, but at the cost of changing the network itself, and then having to do it again iteratively, because the biases are different, the energy landscape shifts a little bit, and that's what makes it an iterative process. And this is very similar to what you just said about the heteroclinic channels or cycles.
Yeah. So no, very, very similar. Yeah. And if I understand you correctly, I think you could also see a connection with linear switching dynamical systems, so that you pursue your linear trajectory until you get to your fixed point, and then you switch to another landscape, another linear system, and then you pursue that. And that's a very common way of modeling chaotic dynamics as well. Mm-hmm. So that sounds very, very similar as well. That would be a sort of a discrete approximation to this to what you were describing in terms of re-evaluating the energy landscape after convergence to your fixed point, which is itself an approximation to actually writing that switching in terms of very brittle dynamics at the point of when you get in the neighborhood of one of these unstable fixed points. Yeah, absolutely. Let me, if you excuse me, let me try and share my screen and just quickly go through the papers that I had. So, some of them might not be relevant because I didn't hear the end of your presentation when I got them up, but I'll show them anyway because they might remind me to say something which might be interesting. Mm-hmm. Good. Okay. Well, yeah. Sorry. So for those people watching the recording, this is the Fernando Rosas paper that Tamas was talking about. So I noticed Daniel Polanyi. So he's an expert in empowerment, a colleague, and Anil Seth he likes greater causality, but doesn't like integrated information theory. So, well, I noticed you put Giulio Tononi down against global neural workspace. Don't do that. He's integrated information theory. Find somebody else for global neural workspace. It's usually Stan de Haan and his colleagues.
Okay.
Yeah.
Yeah, thank you.
Yeah, and Anil Seth would have told you that had he seen the. Right. Okay. So that's just for information that I didn't know about that. Just a very general point, touching upon your last slide, noting that the roughness of the free energy landscape that defines the attracting sets is potentially a very important determinant about how easy it is to jump from one minimum to another stable or metastable fixed point, and how that could be construed in terms of facilitating therapeutic interventions by making it easier to jump from one metastable fixed point to another one. This is that idea has a lot of mileage in the computational psychiatry literature, where the roughness or the height of the free energy barriers can be determined by the precision or the relative precisions, your betas, in the Hopfield net version of the more generic formulation. And I just put this up here as one example of this theme, that precision really matters, where you should tell the reader that you can think of precision as an inverse temperature. So if I reduce the precision, then the precision, it is the inverse temperature. So if I increase the precision, I reduce the temperature, and that means it's much more difficult for me to jump out of one stable fixed point to another fixed point. In other words, if my precision is too low, I am stuck in a rut. And that rut could be obsessional compulsive disorder, it could be chronic anxiety, or in your example, chronic pain. So the therapeutic approach then would be to reduce the precision, because you've got these overly precise free energy landscapes that are keeping you trapped in a particular mode, either perceptual set, attentional set, or indeed a behavioral set, if you're talking about say addiction, for example, or certain avoidance behaviors. And precision is interesting because neurobiologically, certainly predictive coding simulations, but also beyond, the precision corresponds to the excitability or the postsynaptic gain of neural populations, which is exactly where drugs work. It's an important point to make there, that your free energy landscape depends very sensitively on the precision, read as an inverse temperature, and the precision physiologically corresponds to the modulatory excitability or postsynaptic sensitivity to afferent input. Interestingly, psychologically, it probably corresponds to attention. So there's a very closely, if you want to talk about consciousness, then the precision often is read in terms of the attention. So if I'm attending to one sensory stream, I'm affording it much more precision than another sensory stream, or I am not. I was trying to think of the temperature analogy, but I won't. So this particular framing was from Robin Carhart Harris, who's famous for promoting psychedelics as one of the key ways of affecting temperature, beta, or precision, so that you can, in psychedelic states, if you like, emphasize the sensory part of your landscape relative to the constraints you get from very high level precision in deep generative models. So I felt there was a nice connection there with your chronic pain example.
Yeah, definitely. And from the point of view of my of this mathematical framework, so actually it is supposed to be not the precision of the what I call lower level node, but the higher level node or the attractor, where it becomes a bit less less clear how that could be related to excitability, but maybe it's somehow some kind of a weighted combination of excitability in a network of regions that that modifies the temperature corresponding to one attractor or one one aspect to be integrated, which might be, so that also suggests that that there might be, like, for, I don't know, for different diseases there might be kind of another network where we somehow have to target excitability.
Yes, yeah. Well, and that's exactly your. I noticed you'd been reading Mark Soames and emphasized the importance of this reticular activating system and the cells of origin of the neuromodulated neurotransmitters that set the temperature or the inverse temperature or the precision of various neuronal targets. So that, I think that's absolutely right. If you wanted to look at this mathematically, the precision in question is the Fisher information metric on the statistical manifold of the news. So you could, in principle.
Sorry, I didn't hear the last sentence.
Sorry,
could you repeat?
The precision corresponds to the Fisher information metric on the statistical manifold over which your mu or your internal states play. So even if they are invisible or latent, there should still be a mathematical definition, and in principle you should be able to estimate the precision of the high order, the beta kind of precision. So that would be a mathematical one. In predictive coding schemes where the mu are explicit, then that it is those in those schemes that you would associate the precision with the sensitivity of the error neurons. Remember, in your three, you had your three nodes for predictive coding: predictions, observation, and error at the top. So you can imagine the precision really being how excitable is that prediction error, but you have to imagine a hierarchy of these. So you've got basically the observation is, if you like, a prediction error from below, and then another prediction error providing, so if you have a hierarchy of these triadic nodes, then each level has its own precision of the prediction errors, and that in neurobiology and in philosophy circles is why people talk about precision-weighted prediction errors. So these are beta-weighted prediction errors, but you have to define at what level in the hierarchy you're talking about. You're absolutely right. So it could be sensory precision, or it could be a deep prior precision if you've got a deep Hopfield network or a deep a deep restricted Boltzmann machine, but that you can write down in terms of prediction errors. But I wouldn't worry about it too much. I think it's just the basic idea, just joining the dots of people that
but it's very stimulating.
Precision is very important in shaping the free energy landscape, and the shape of the free energy landscape matters in terms of how easy it is to move around that free energy landscape and have different beliefs or different behaviors. One interesting thing, that this is not really, it didn't really come up in your presentation, but one mathematical and interesting consequence of the free energy principle itself is that the point attractors or the line attractors at free energy minima are always sitting in landscapes of low curvature or high precision by construction. So this is not the thermodynamic free energy. It's not necessarily even a Hopfield or Boltzmann kind of energy. The special thing about Bayesian networks is that the energy functional is the variational free energy. And the variational free energy has part of it the entropy of your estimator. So you're always looking for the least certain estimate. So you're not committing to a particular value. And this is due to James's maximum entropy principle. So you can think of the variational free energy principle as dual to James's maximum entropy principle. And what that means is the free energy minima always have the smallest curvature. So you're maximally uncertain about the actual where you are in the landscape. And that's what I meant before about the precision measuring the curvature or the Fisher information metric on the statistical manifold. So this is important because it allows you to bring in James's maximum entropy principle and the free energy principle to say that the free energy landscape around the attractors is quite flat. And that's interesting because it's flat. It means it can move around quite a lot without changing very much. And that's one picture of self-organized criticality, that you get basically your center manifold, as it were, now has it's slightly more encompassing, and it allows you to wander over the inertia manifold, so that you would expect to see critical slowing. You'd expect to, so very much in the same way that you can talk about the mu's as order parameters, as slow, unstable states. The slowness can also be interpreted in terms of self-organized criticality, in the sense that you're now allowing yourself to wander around very, very low curvature basins or minima on your free energy landscape. Or when I say one, yeah, so you can take local excursions without changing the free energy very much. And that has some interesting implications in terms of self-organized criticality and critical slowing, which people like Michael Brigspin, Gustavo Deco, certainly Gustavo, very much focusing on in terms of the itinerant aspects of this, which is another way of eluding the detailed balance approach. But I thought you might be interested in that, just because it has some. There's something special about the free energy landscape that you won't find in neural networks or Hopfield or restricted Boltzmann machines, because they don't represent uncertainty. So the proper way to do this, the way the brain does this, is to represent uncertainty in accord with James's maximum entropy principle. So you add the accuracy, you add the entropy to the accuracy, you get the free energy, and that means that your double well, for example, means it has to be the case that at the bottom of the two wells, things have to be relatively flat. You can't get sharp minima by definition, by construction. So you can't get trapped forever in a very sharp minima, by almost by construction. So I find that a really interesting mathematical point, but perhaps for you it's one story too far. Yeah, I just put this in. This is a nod to Walter Freeman, who was one of the good and great of nonlinear dynamics in the brain. So I don't, you've heard of him, yeah. Yes. So this was the very first paper that we wrote on attractors as the basis of predictive coding, but it was actually, that doesn't say so explicitly, but it was meant to be I don't have it here. It was meant to be a celebration or a festive for Walter Freeman. So that's where this originally came from. Is to right, yeah. No, there's not much. But it just sort of. This is not point attractors, though. This is chaotic attractors. But perhaps you could use this just to say exactly the same machinery can now be generalized not to point attractors, but to deterministic chaotic attractors. And then you can say that this, and also this can be formulated as a predictive coding scheme, should you want to. Now, the reason I put this one up here is a very specific reason. So this is a recent paper, Pathinterple's Particular Kinds and Strange Things, by me and my colleagues. But what it shows is that you only get interesting, slow, planned, deliberative behavior under particular assumptions. And one of those assumptions is exactly the same that you made, which is the delta function relationship between the external and sensory, and between the internal and active states. So if you wanted just to have a throwaway comment, following Friston et al., we make the same conservative assumptions and assume that there is no uncertainty in these particular mappings, we arrive at a much simpler functional form for the dynamics under a particular partition. So this just takes you through. Yeah, so what this paper's trying to do is just look at various limiting cases, and the first and most important one from your point of view is, my apologies, is a conservative particle, and that basically, yeah, so when the particle follows paths of least action, which basically means the random fluctuations can be ignored, which is what you've done basically. Yeah, so your first assumption of that delta, those delta point masses, I think is perfectly plausible, and indeed is a necessary assumption if you want to talk about systems that pursue expected free energy. And that's relevant because you're absolutely right that systems at a different time scale maximize their expected free energy with respect to their parameters, say W, will orthogonalize. Because as you pointed out, well, perhaps you didn't point it out, but the expected free energy just is the mutual information minus the expected cost. And in the absence of any expected cost, the maximum of the mutual information is going to be one where you've got an orthogonal representation.
Okay. Okay. I just wanted to get back to this orthogonal thing with you, but yeah. Okay, that's also very enlightening. Although I feel like I still have to go a little bit into the details with this paper. I started to read it a couple of weeks ago, but didn't get until the conservative particles.
All right. Yes.
So,
yeah. Well, this is very dense, and it's full blown physics. So it takes it's the summary of decades of thinking about this. So do not expect this to be an easy read, but it might have some bits which you find quite useful. And I thought this was particularly useful for you because it does really simplify things. For this paper, it doesn't simplify anything, but it allows you to talk about expected free energy. But for you, it just allows you to.
Could you just repeat again what you said about the orthogonality? I felt like I understand.
Right.
I couldn't say it again. Although I will have the video recording. So
yeah. Well, it's not covered in this paper, but if you have a conservative particle, then you can show that its dynamics will maximize expected free energy. The expected free energy can be expressed in terms of an expected cost plus this, which is an expected information gain. This expected information gain just is the mutual information between sigma and mu in your setup. The mapping W that maximizes the mutual information is orthogonal up until a rotation. But if you put, up until a rotation. So if you assume that the W are also latent states, and the particle is, or the system is conservative in the sense that you've applied your delta functions, you can say, I'm not saying you should simulate this or show it mathematically. You can just say, we will assume that under the conservative assumption that the system, the parameters of the system, which are slow states, will maximize their expected free energy, or namely the mutual information. That assumption implies, the conservative assumption also implies that it is plausible that the W's will be orthogonal, because that's the maximum mutual information.
That's beautiful. I was like, that was one of the parts about the orthogonality of the attractor states that was kind of the hardest to digest. So I started to, when I was working on it, I started to see that okay, but in this case, the whole thing will basically boil down to principal component analysis.
Yes.
And it was, I almost got sad about that for a moment, and then I realized that okay, but with a whole lot of understanding about why it has to be principal component. So
I see.
I think it's not bad to have a simple solution if we understand.
Well, I mean, again, you should explain that. Why has principal component analysis been such a useful, such a popular tool for nearly a century?
I tried to argue along those lines, and also like based on literature which shows that, like, in terms of Hopfield networks, it's called the projection Hopfield network. And it's the best what you can do with that type of architecture. So like no spurious states, fast convergence, a maximal capacity, memory capacity. So I try to argue that, okay, then it kind of makes sense that that evolution takes use of this efficient implementation. But what you talk about it here sounds like a whole lot of extra insights. I will definitely do a deep dive here, even if the math is hard to digest or take
Okay,
some time.
right.
But
Well, yeah, well, don't take too long. But if you wanted to do a deep dive, there is another paper which is not here, which uses numerical studies to show that the mutual information is an emergent property of free energy minimization under conservative assumptions, namely that you can change the parameters to maximize expected free energy, thereby maximizing orthogonality, or at least maximizing mutual information, which, as you say, means you've got to have, spanning the right orthogonal space to do that. No, I won't do that. You've got enough deep diving to do. You deep dive on this paper, and then you can worry about the.
I definitely not in terms of this paper, but that's something I'm just personally interested in. Why it has to be orthogonal? So I just found it puzzling why it has to be that. I mean, it looks nice, but I just yeah, I just want to know about it personally. Want to know more about it personally because for some reason I find it very interesting.
So you'll find this bit interesting because it sort of joins the dots between strange attractors that have this sort of fractal strange aspect, but also connects it to Hofstadter's strange loops and the like. But this really does depend upon the conservative part of the flow, which is this anti-symmetric part. But if you're just interested, then this has got lots of interesting bits to it. So that was the strange things paper. Yeah, and then these are just two technical papers which speak a lot to your analysis. This one is probably you know everything in this paper, but if you just wanted to find if there are any other words or rhetorics or expressions that would provide a complementary description, but its basic story is effectively covering that aspect that we were talking about before about criticality and low curvature free energy minima, and unstable versus stable or fast versus slow modes. But the key point about this paper was what is this about? The key point about this paper was the equivalence or the benefits and costs of assuming a symmetrical asymmetry between effectively of the Jacobian that inherits from a symmetry in the W's. I can't quite remember now what where that was expressed, but it did remind me. Your derivations remind me very much of this treatment of eigenmodes in the brain. In terms of interactions between nodes on a graphical model of resting state fMRI. So I felt that might be interesting. So that's on nodes and modes, written with Olaf Sporns, who was one of the the inventor of the connectome in America. But more interesting is this one. So this one speaks to some of the issues you were talking about, but what this basically does is it does a multi-scale analysis based upon fMRI data and empirical estimates of the Jacobian, decomposing both in terms of Markov blankets, but from your point of view, more interestingly, in terms of symmetric and anti-symmetric parts, and going through looking at the different scales of coupling that one can get. In fact, using the rhetoric of so here the equivalent sort of connectivity at a very fine scale, moving through to coarser and coarser scales largely to the scale that you were more interested in. But the key point that this paper brings to the table was the was the understanding the importance of the Helmholtz decomposition in terms of statistical physics and the symmetrical and anti-symmetrical parts of the effective Jacobian, and how you can even you can even get a Heinsberg uncertainty principle for your fMRI time series should you want to. Oh, here we are. So this is very similar to your derivations here, but you can tell another story for physicists about your fMRI time series in terms of momentum and temperature and the like, and the decomposition into sort of dissipative and non-dissipative parts. Taking people through the hand about the relationship between the solenoidal part and the non-equilibrium steady states, formally and also anecdotally with a worked example here, which is not one of your networks, unfortunately, but I'm sure you'll be able to spot the. Yeah. Okay. So I thought that might be a useful section just to, I repeat, provide another language or another perspective on the importance of the symmetry constraint and what that would mean in terms of the class of systems you're dealing with that introduces this equivalence between dissipative, non-dissipative, detailed balance, non-detailed balance, and how you can interpret that in terms of the kinetic energy of your modes with dissipative and non-dissipative parts there. So given your mathematical fluency, I thought you'd enjoy that. And that's parcels and particles in the brain. Yeah. Excellent. Good. That.
Wow, thank you. Thank you. That's I think this is exactly what I needed with this project right now. So this is exactly what I I wanted to have. It's just that there are now so many thoughts in me. So of course I will start reading about all these. If it would be fine with you, I might bother you again with a couple of follow-up questions afterwards. If it's not too big of a favor, because
no, not at all. Yeah. I think that what you should do to guarantee my availability is feel free to drop in on our methods clinics at 12:30 p.m. on Mondays. So that you could do. Myself and Peter Ziedman are just sit, we wait for, and Johan, and we just wait for questions. So first come, first serve. So if you have any technical questions, then you can always find me at 12:30 UK time Monday on Microsoft Teams.
All right, same link actually as this.
I don't think it is.
I will ask for that.
Yeah, you let me know and I'll email you with a copy of the link and a copy to Peter, who chairs the meetings. Yeah.
Great, but it will take a little bit of time for me now anyway. But yeah, thank you. That's great. Yeah, what I will also have to think about is like, it's not that much about the science part, but you also mentioned it a little bit. But I just wonder about the right strategy to publish this, because there are many sites, I feel, and I don't want in this publication, I don't want to spare the math part. I think it's just so essential for making these insights. On the other hand, the whole project is in mind with basically the neuroimaging people, like mostly like experimentalists, because I just feel that this could very, very quickly result in something that is that changes a couple of things in terms of interpretation, and might provide some new methods that are worth trying with neuroimaging data. I just wonder what could be the good balance between all these aspects. But
well, I think if you establish the technical stuff in the technical literature for the mathematicians and theoreticians, then you've got something to refer to, so you don't have to frighten off empirical psychologists and neurobiologists who want to then you can just refer to the maths and say, but what that means for you is blah 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 blah, and then you'd be writing something like
split it, or like outsource.
Yeah, and probably more than just split into two, probably 3 or 4 different papers, all saying similar things, but in different languages with different levels of technical depth. So you want a paper in network neuroscience, you want a paper in Royal Society interface, you want a paper if you can get it into Nature machine learning. You want to say neural computation, probably a better. And then you want a paper in Nature neuroscience or eLife or imaging neuroscience or neuroimage. So you've got multiple communities and levels, but I'd start off with the technical stuff because then you can refer to that without using any maths when building a story, a more narrative account for people, empirical users. Having said that, I'm going to ask Christoph what his advice would be if he had to pick one paper to read. Which journal would he go for? What kind of paper would it be?
Well, I'm not too sure I'd have the most useful advice on this. So I don't think I can recommend or have a particularly useful opinion on this one. I'm sorry.
What's your favorite brain imaging journal?
Well, I don't want to sound too cliche, but well, in general, I really like. It's not in particular about neuroimaging, but I do really like nature and nature communications. Just the simplicity in general with which typically papers are written. I just really appreciate that. Yeah. But I realize this is this is probably quite a cliche answer. But like from my perspective, I mean, I just finished my master's, so I'm just fairly, and I've done something else before, which was fairly outside the field of neuroscience. So I'm still very much joining the field. So yeah.
Well, that's good advice. Nature or nature communication.
Which I'm not too sure. It's a secret tip.
I wanted to aim higher, but
He's being ironic.
Right. Then yeah. Is it? Sorry, I didn't want to. I did.
No. You have to send us home, but you have to invite us.
Is it a wrap? Yeah. Thank you. Thank you so much for this intimate session today. Thank you so much for your brilliant presentation, Professor Spisak. Thank you very much for the extensive discussion afterwards, Carl. And I guess then we can all just leave into a lovely afternoon, evening. And yeah, I thank you very much again. We have another session tomorrow, which will be chaired by Miguel, and I'll be back, I think, in 2 weeks or something.
Yeah, well,
so thank you very much, and hopefully see you soon.
Yeah, thank you for the interest, and it was really very stimulating. Now I will have to digest it for 2 weeks for sure, but it was extremely helpful. So thank you very much, and I wish you a lovely afternoon.
Bye-bye.
Thank you so much. Bye. Have a good evening.
Bye.
Bye.